Hey everyone, good to have you here. It's the start of office hours. We're going to start up with some project stuff. William was wondering, can we go over the sample t-test for the project? So let's go ahead and take a look at a sample t-test. Let's hop to the main screen. Let's do this. So to do a t-test, we need quantitative data. So we're going to go here to the analyze distribution option to go ahead and look at. Can we give an example of what you would want in the interpretations? Yeah, definitely. Let's do that. Great question, Layla. And so we have right here the distribution where we're going to take a quantitative thing. These are women of the Pima tribe, I believe. I've got it marked in the data set what it is, but this was data collected on women of the Pima tribe. I also have quiz. Yeah, anytime. Let's do those next year. You got it. And maybe we want to see, we want to look at the average amount of time these women have been pregnant. So we have a variable right here on how many times the women have reported being pregnant. So we want to see what is the average. And so this would be for all women in the Pima tribe, because this sample is from women in that tribe. And let's take a look. And wow, that's a pretty right skewed distribution. Lucky for us, the sample size is 392, which means we would meet the large enough n, which can be used as part of the nearly normal. We talk about nearly normal being for t-tests or t-intervals, but we don't go into too much detail on the conditions because I've read statistical reports and people usually don't write about the conditions. They might say something like conditions were meant to run the test, but they're going to rarely go through and walk you through each condition. But this is a very right skew distribution, but because we have a large sample size, we're probably good and the distribution will be nearly normal. It's going to have some right skew, and once again, to review, things we should know for the test is we could look at things like the normal probability plot, and you do see the right skew right here. We could look at the goodness of fit test, we could look at the histogram, but because the sample size, you bet, Carly, you got it, we'll do this, then we'll do latest question, then we'll do Carly's, you got it. So overall, because the sample size is so large, we are pretty good on it being nearly normal because of the large sample size. You do have a 95% confidence interval right here, and we're going to see something really interesting. If someone said to you, I think the truth for all women in this group is that they've been pregnant 3 times, would you believe that value or not believe that value, Layla? Would you believe that? And William was asking it too. And Carly, would you believe 3 or not believe 3? So just look at this interval where it would be, I am 95% confident the true mean amount of time for these women being pregnant is contained in the interval 2.98 to 3.62. 3.62, yep. I am 95% confident the true mean amount of time that these women have been pregnant is contained in the interval 2.98 to 3.62. Would you believe the answer of 3? Would you believe that or not? You would be like, I don't believe 3. 3 doesn't seem like a possibility of truth. I don't think 3 could be the truth for it. I would believe 3, and this goes to the end of class today. The reason we're able to believe 3 is because it's contained in the interval. So let's go ahead and do the t-test on this. The t-test right here is done with the test of mean, and it should say right there, it says t-test, yep. We're going to test the value of 3. Remember, 3 is contained inside the interval. And so when you look at the results right here, you'll see on the does not equals test, you get a p-value of 0.0642. So if we're doing the alternative for the does not equals test, which is the two-tailed test, you can see the p-value for it down here, we would get right here a p-value of 0.0642. So questions were on the interpretations. How would we interpret this? Well, first, let's mention the p-value. With a p-value of 0.0642, I fail to reject the null hypothesis at a what level of alpha? Now, what alpha level do we generally use? So I'm using this p-value right here to say, with a p-value, so we definitely need a screenshot of this, with a p-value of 0.0642, I fail to reject the null with my alpha level of what? My alpha level is where I reject the null, and I'm saying using an alpha of this, I would fail to reject the null. Using alpha of this, so my p-value is what it's decently above this. Doesn't matter how far above, just matters if it's above this or at it. 0.05, yep. So since my alpha level is 0.05 and my p-value of 0.0642 is above this, I fail to reject the null. So that means I would continue to believe the hypothesized value of 3. So I think 3 could be a truth. I think 3 could be the true mean amount of time these women have been pregnant. Is that making more sense, Layla? And this is why the test and the interval converge, which is a question you have to answer. It's because the tested value was contained inside the confidence interval, so you cannot reject a value, and it's a 95% confidence interval. Thus, we could not reject this at the 0.05 alpha level. So that's why on the two-tailed test, which this is the two-tailed test, just to make that clear over here, when you're looking at the test results, this is the does not equals 2 test, this is the greater than, and this is the less than. And you'll notice that the less than, which is this area right here, is the very large amount of shade area, 97% of the curve. And the greater than test is going to be the area right here, which is the smaller area. The does not equals test will then be double the test. Hopefully, and I'll zoom in on this just a little bit right here so people can see, but seeing these results right here, seeing how they coincide, hopefully should make sense with today's class, where you can see the greater than test, the less than test, the does not equals test, and seeing how the relationship they have with double the smallest and these two add up to 1. Is this making more sense right here and knowing what to interpret on the project and how to interpret your test result to say whether you reject the null or you do not reject the null, and how to interpret your interval to talk about I am 95% confident whatever you're talking about is contained in the interval blank to blank? Hopefully that makes more sense on the project. I know William and Layla were asking about that, but that's kind of interpreting the one sample T for the project. We did some two sample T during class today. I mentioned, and I kind of interpreted those results. So the two sample T was done during class today, and we could talk about that a little later too if you want. I think Layla has the next one. Which one were you? I can pull up quiz number 9. Carly was wondering about Canvas quiz number 9. And so Layla, if you put a question in the chat, go ahead and put a question in the chat. And really? Okay, let's take a look. This is what we just covered today stuff. Oh my gosh, we gotta do some calculations. We might have done this one yesterday. We'll do this right here. It's the 1980s. It was generally believed that congenital abnormalities affected. Yeah, let's do that next year. You got it. Let me, 2 seconds. Got so many windows open. Okay. Ready to go. We'll do one version of this and we'll hop over and do the 1980s question. So this question I think we did yesterday, but let's do it again here real quick. A new diet is being tested. The inventor claims that people lose 10 pounds on average after 6 weeks. 25 people are randomly selected, randomly picked to try the diet. Researchers are concerned about the inventor's claims being exaggerated. The sample yields an average of 6.9 and a standard deviation of 7.4. Calculate the appropriate test statistic. So with this right here, no, I changed one of the questions. Yes, if you saw yesterday. So the test statistic right here was something we covered today in class. We need the following equation. We're testing how much weight people lose. So we need y bar minus mu naught, because we're doing a t-test here. This has n minus 1 degrees of freedom. And we do s over square root of n. So Carly and everyone, I need some help here. I need to identify the notation. So that is all the notation on the screen. You see, we need 4 things. And we're trying to find this t right here, this t-test statistic. So what are the 4 things on the screen, and what are they going to be? So what are the 4 things on the screen? Like, we need to find these values. So we need to find y bar. We need to find mu naught. Mu naught is the hypothesized value. This is whatever they're testing is equal to true. And you'll see, especially with this one, we would have the null hypothesis states that the true mean is equal to some hypothesized mean. And the alternative hypothesis would be that the true mean is, this one is saying, are the claims exaggerated? So less than. So what are some of the values right here? And we'll plug them into the equation, and then we can solve for the t-statistic. So one of the biggest things is knowing your notation. We just keep saying that, like, know the notation, know your notation, know which notation that you have. If you know the notation, questions just get way easier, because you're like, oh, that's the y bar. So, yep. So switch it. Switch it. You're really close there, Layla. This is the hypothesized, and this is what we saw in the sample. So that's the sample, and then that's the sample. Yep. You're seeing it. You're seeing it. And it's just a reversal of it. Yep. Because this is what we saw in the sample. It's always observed minus expected. It's just like z-scores, where you take the observed value minus the expected. Yeah, no, this is the practice. You got it. And there we go. It's square root of 25. And so let's go ahead and take this. And 25 square root I don't know why I did that. There we go. There's that. Is that really it? Is that the crazy number you're going to get? Tell me if I'm wrong. I think yesterday we got a much nicer number. 7.4. It looks to be it, right? Yeah. As far as I can tell, that's right. 2.09. I'm worried I made a mistake. Round to 2 decimals. 2.09. There you go. Now, this one I made a little change to yesterday. They wish to show evidence people are not losing 10 pounds on average. So I literally wrote this yesterday to help out with the version of it. So what we have right here is they wish to show evidence people are not losing 10 pounds. So the alternative... Oh, did I do? Yeah. So here. We should have a does not equals, I feel like, but it can only be one of these two. People lose more than 10 pounds. Yeah, I think that's where I got. Would it be negative? I think it's positive, right? Oh, it is negative. Oh my gosh. Holy mackerel. Layla, you are correct. Thank you, Layla. Let's throw some 50 points. Mubot's awake right now. Layla, you are 100% correct. It is negative. That's a pretty big error right there. Great catch, because this top part will come out to a negative number because we are below what we expected. So it is a negative t-score. Great catch right there, Layla. It is negative. I was doing the top portion in my head. It is negative. Great catch right there. Yep. I'm capable of making errors, and that would have been a pretty big one right there. A smaller p-value provides stronger evidence against the null. So when the p-value is small, what do we do to the null? We reject it. So when the p-value is smaller, we need to change that. We do have more evidence against the null. Low p-values are evidence of... True or false on this one? True or false? Just this, I hope... this hurts me. Whenever someone gets this question wrong, this music plays in my head. Low p-values are evidence of cause and effect. When someone gets this, if you get it wrong, don't worry. It'll just hurt me. Low p-values are evidence of cause and effect. Like, if someone said this, like, I'd like, no. This question right here should be a gimme on the test. It should be like, you should see this question. Yeah, this is false as false can be. Now, this is something we'll cover tomorrow. I was hoping we could get to it today, but I don't like to rush through material. I know you'd be like, Brian, we do a lot of material. I'm like, yeah, it's 3-hour class, a lot of material. In a type 1 error, the null is what? Who can tell what this means right here? In a type 1 error, the null is what? Think about what this letter Brian is making right here and what that stands for. In a type 1 error, the null would be this. In a type 1 error, the null is this. Now, we're not talking about type 1 yet. Not talking about type 2. But in a type 1 error, the null is true, and we reject it. So in a type 1 error, the null is true, and we reject it. That's a type 1 error, which we're not talking about right now. In a type 2 error, the null is what? And you'll see this a lot tomorrow. In a type 2 error, the null is false. And you see the second one right here? And we fail to reject it. So you'll see me doing this tomorrow. In a type 2, the null is false, and we fail to reject it. In a type 1, the null is true, and we reject it. In a type 2 error, the null is false. That's an F, and we fail to reject it. So quick way of memorizing it. I've had people who teach statistics being like, hey, I'm going to use that because it's really easy to remember. In a type 1, the null is true, and we reject it. In a type 2, the null is false, and we fail to reject it. And we should get that 100. Don't tell me we got something wrong here. 10 out of 10. That's what we like to see. The streak is back. We got one question wrong in like a week. It was this one we got wrong yesterday, and that's why I changed the wording. They want to show evidence people are not losing 10 pounds on average. So they're trying to show evidence that they're not meeting their goals. So I think we selected that they were trying to show evidence you lose at least 10 pounds, but I made it a little more clear. They want to show evidence, which is the alternative. So I added this to the question yesterday because I was like, that's not clear enough. But they wish to show evidence people are not losing the 10 pounds. So they want to showing that it's less than. Does that make sense why I chose the less than right here? I'm glad there wasn't the does not equals to, because then there'd be, you can either lose 10 pounds or not lose 10 pounds. But they are losing less than 10 pounds. I just didn't want to put less than because I was like, that makes it too obvious. Then you just choose less than automatically. They want to show evidence people are not losing the 10 pounds. So this would be the alternative they're looking for. And that's the one I got wrong yesterday. So I changed the wording to make it a little more clear. And now we're going to do, let's hop. Oh, I didn't put a cut in the video. I think I put a cut in the video. I think I did. Let's go and get Layla's question right here. I'm also out of coffee again. In the 1980s, question. We got radioactive fallout. Got so many questions. Here we go. Here we go. Let's do this. In the 1980s. Let's head back to the 1980s here. Here we go. Okay, we're back in the 1980s right now. It was generally believed that congenital abnormalities, birth defects, affected about 7% of a large nation's children. Some people believe that the increase in the number of chemicals in the environment has led to an increase in the incidence of abnormalities. A recent study examined 410, that sounds like a sample size to me, randomly selected children and found that 30 of them, that sounds like an X to me, showed signs of abnormalities. This is strong evidence that the risk has increased. Ooh, so what do you see right here? What sign are we going to look for? It says evidence, and that sounds like an alternative. So what sign are we going to look for in the alternative right here to narrow it down to choices? This will narrow it down to 2 choices because we're going to look for the what sign. We know the null has the equal sign. That information does not help us because all the nulls here have an equal sign because the null always has the equal sign. We're going to look for the greater than, and that narrows it down to choice either A or C. It's one of these 2. So now we need to find the null value. The null value is what we start out believing is true, and it is A. Because we believe at the current time, it was generally believed that 7% is the truth. These numbers don't highlight because they're the ones that augment, change, or not augment, but change when you do the problem, because they can change it to different values. So this is what is believed is true. And that's what we're hypothesizing is true. That's P naught right there. And so with that being P naught, I guess let me do this. There we go. There we go. I think that'll work right there. So with this being P naught, I'm not used to that. I'm changing around volumes right now so I can hear different things. I have a question on, yeah, of course, Caroline. Put in the chat. We'll do it next. You got it. Check the assumptions. The assumptions right here are random. One random. We need less than 10% of the population sampled. They separate out the independents sometimes. I won't do that on the test. I just call it random. If it's random, it's independent. They sometimes pull those 2 apart. We do want more than 10 successes and failures. Yep. To check for there being at least 10 successes, at least 10 failures, technically we'd need to take 0.07 times it by 410, and that's at least 10 successes. At least 10 failures is 0.93 times 410. This is NP naught and Q naught, and they are both greater than or equal to 10, so we are good. And yep, we want there to be at least 10 successes, less than 10% of the population sampled, the independents and random, and they pulled them apart. I usually just do random as one condition. Now the p-value is a jump right here. What do we need to find? I need someone to put one letter in the chat. What do I need to find before I send my decision on Discord? Yeah, definitely. I can take a look after some officers. You got it, Ritu. Did great work. What do we need to find the p-value? And you can see the steps we were doing during class. I need you to put one letter in the chat to tell me what we need to find the p-value. And you can see the steps. We've already written the null and alternative, and they want us to find the p-value. Oh, let's do the radioactive fallout next. You got it. So they want us to find the p-value, but you say, well, Brian, first, slow down here. Find your what first. Before finding the p-value, you have to find the this. Before finding the p-value, you have to find the this. The z-score. Great job, Layla, right there. So let's go ahead and try to find that z-score for the problem. To find the z-score, we're going to take the information right here. I'm going to bring it over to a new sheet. And let's take work on this. Let's go ahead and check it out. We have right here 7%, 410. Oh, that's just the alpha level. Yeah, we'll mark it. That's alpha. And I think that's got it. So we have here p hat minus p naught. Go ahead and just tell me one of these. Just tell me one of these, like, if we can have people tell me 2 of these, like I'll tell you a few. This is their alpha level right here. They're saying alpha equals 0.05. That's when they're going to reject. What else do we see here? Any other notation you can tell? It's tricky because I've got a lot down here. I've got P hat, P naught, P naught, Q naught, and there we go. Layla's finding right there. That's excellent work right there, Layla. That is N, that is X, and X over N equals P hat, which is the sample proportion. We're just seeing what proportion of children had birth defects. And so we get 30 over 410. And so 30 over 410. And that's that right there. Great job. Leo's got it in the chat. You know what's interesting? They actually give that to you as one of the values in the fake alternatives, and that is P hat right there. Excellent job. And then P naught is going to be this right here. P naught is equal to 0.07, which Q naught is going to be the complement of it, 0.93. And so great work, Layla. I know this was, and technically that is P naught though. Technically it's P naught. Because it's the hypothesized value, which we are saying is equal to P. So you might be like, well, aren't we saying it's equal to P? Yes, so it is also what we assume is P right now, but it is P naught. And so that is the hypothesized proportion. So let's go ahead and solve this. So there's not much of a difference right there. We'll find out if the difference is statistically significant in a moment. And P naught. Reese cracking me up right there in the chat. Let's throw out some more 50 points. Great work, everybody. Great teamwork. This is what we like to do. Practice the work and get it down. Okay, so P times P naught times Q naught. What are you doing? I'm over here. P naught times Q naught over N square root. Also on the playlist, single mean, the same thing as one sample, and the two sample means the same thing as two sample. Yep. The one sample mean is just single means and two sample means. Does that make sense for you too? So it has the, like a one sample t-test, one sample t-interval is one mean, two sample t-test, two sample t-interval is two means. I think I did everything here right. 0.07317 minus 0.07. Ooh, that's tiny. That's a tiny z-score. So with that being a tiny z-score, that means the p-value is going to be much bigger. So since the p-value is going to be much bigger, we're not going to reject the null right here. I hope I didn't. Yeah, they're really close. We'll get that David M. Lane applet in the chat. We've already got it right here. We're doing the does not equals. No, we're doing the greater than test, right? So since we're doing the greater than test, we graph to the right of it, and I didn't copy it. There we go. It's 40.07. I don't know if I'm doing my wrong, but my z-score is really, yeah, sometimes it'll be really big. What was your p hat and what was your p naught? You can get a really big z-score for this. Just tell me your p hat and your p naught, and I'll tell you if it makes sense what you're getting. Which may have done it wrong. I'll tell you if it makes sense on what you're getting. 0.40, 3 decimals. I think that's right there. Carefully explain what the p-value means. It's the probability of observing what we observed or we observed. My p hat is this, and my p naught. Yeah, that's pretty far away. That'll give you, and then your p-value is going to be 0 basically. I think your p-value will be about. You can tell me what your z-score is, and I'll tell you what your p-value should be. Just go ahead and say, like, I got a z-score of this. You're probably going to, if you get a z-score like 5 or 6, your p-value will be 0, basically. Observing 30 more children. Yeah, here we go. Given the null is true. The probability of observing what we observed or something more extreme, given 7% of children actually have genetic abnormalities. And what do we do right here? We fail to reject the null. There is not evidence for the alternative. Do the environmental chemicals cause changes? Yeah, it's going to be a p-value of 0. The p-value for that's going to be 0. Is unknown because the hypothesis test does not affect cause and change. Ooh, God, get scared there. Get scared after you miss one. You're like, what? So we can't do cause and effect. And that literally goes back to the Canvas content we were doing just a moment ago. So you can't show cause and effect by just doing observational studies. You have to do experiments to show cause and effect. So we fail to reject the null because the p-value here is so high. And I think in Layla's, she will reject the null. And you'll still have the same idea right here with the p-value being the probability of observing our results or results more extreme due to random chance variation in samples given 7% is the truth. And what I saw was very likely. And you can see by Layla's z-score in the chat, her z-score is very far away, making it very unlikely. And you'll need to go here to the David M. Lane, which links in the chat. Mubot? Was Mubot giving out points? Mubot not awake? Mubot fell asleep on us, everybody here. Breaking the world, Mubot. Mubot, why are you not awake, man? Oh my god, it's evil Mubot here. I gotta make it so he appears on the screen too now. Evil Mubot on the screen. Trying to do some... Put good Mubot behind him. There we go. He's awake now. David M. Lane in the chat. Isaac, so good to see you, Isaac. Let's add some more points. Add a new addition to your live session. Yeah! Have you not seen Mubot yet? We're throwing out some more points right here. So Mubot should be awake right now, and he's posting... For some reason, he posts things here faster than I see them. So yeah, we got Mubot here.
I am Mubot.
He talks to us. Never seen Mubot? Oh my god, there's evil Mubot. Wait. We get... There we go. Lots of changes to do. Lots of changes. And so I think Airline had a question. Let's have her space. Put on our classic music. Let's put on Celeste music. We rarely listen to Celeste music. Oh, thank you so much, Isaac. So glad to hear that. Glad you're liking all the changes. The background's breaking. I'm going to switch to OBS here when I have a break to kind of make changes. During the weekend, I've got a list of things to do. And Airline's public relations, you got it. I think we've got Caroline's question about radioactive fallout. Amazing stuff. Amazing. Let's go check out some radioactive fallout. Here we go. Heading over to the question. Let's do it. UTK. Aw. Thank you so much. I appreciate that, Isaac. Just continuing to try to stream better and better. We just do new things. You know how it goes. Thank you, Isaac, so much. You're always welcome to swing by and just miss having you in class. Miss talking about like Isaac games and stuff like that. Because every time I see your name, I think of like Isaac, the game. But yeah, thank you so much, Isaac. All the positivity. And Isaac, did you look at your points? I'm trying to think what points you're at. I probably reset your points. Let me fix your points, Isaac. Really quick, fixing Isaac's points right here. Isaac, we're fixing your points. Yeah. I think you were here, Isaac, before... Let's just put it right here. Okay. I have fixed it, Isaac. Your points are now fixed. I don't know if Isaac will check them yet, but Isaac's points have now been fixed. Good. Let me go back here to quotes. Yeah, I think Isaac took the class before we had Mubot. Now we have Mubot. We're always trying to update and change things. Alan, what's up? Thank you. I appreciate that. Did it just a few days ago. Here, watch this. You ready for this? Hey, everyone. Welcome to Stat to One. How are you doing this morning right here? How's everyone doing? Everyone doing all right? I think I got something in my hair. Just 1 second. 1 second. Real quick here, everyone. Oh, man. Check it out. Instant haircut. All right, let's do this right here. I'll get serious. Time to get serious here. Fun's over. Serious time. I didn't move the microphone out of the way this time. Cuts the effect. Okay. We got some other videos. I just have to cut them together. So we got the radioactive fallout question from testing atomic bombs drifted across a region. Oh, so much fun. That's sarcasm. There were 220 people in the region at the time, and 34 of them died of cancer. Cancer experts estimate that one would expect 30 people to die of cancer deaths, because it's unfortunate, but it happens. In a population, in a group this size, assume that the sample is typical of all groups, so it's like a random sample. It's kind of what we assume right here. Is the death rate unusually high? Does this prove that it will cause an increased risk. So are the conditions met? Are these random? Is it less than 10%? Do we have enough success and failures? We do see that we would expect 30, which is more. I hope that will show your office hours 6. Oh, that's awesome. Yeah, yeah. I will still have time to do our office hours after next Thursday. I'll be in London. Yeah, that's awesome. Congratulations on the internship. Congrats. You're going to be in London on an internship? That's super cool, Alan. If you want to say what you'll be doing, congrats, Alan. If anyone's in the chat wants to throw some congrats to Alan, I think Layla's still here. Carly might still be here. But congrats, Alan, so much. Like, that's awesome, man. I love people coming by and sharing these successes. Colin was talking about he got something at Disney. He's doing an internship there. So I really love hearing these success stories from students. But Alan, you're super talented, and you got to keep sending me K-pop videos. So I appreciate that. This is an interesting question. This is an interesting one. Because we have right here the sample size. We have right here the X. And then this is kind of X naught. So I'll be working on a fintech company working with data sets and whatnot. It's almost like doing something similar to business. Yeah. What's your major, Alan? What are you majoring in? I'm going to find P naught right here. So that's just, this question is weird because P naught is going to be this. So P naught is what we would expect. And we would expect, it sounds like you are doing something similar to business analytics because a lot of things are very. I'm sorry, like Brian. Come on, man. I'm business analytics. You know that, man. Yeah, it's a lot of data analytics. When you say I'm doing something similar to business analytics, I'm like, well, not right. You confuse me, Alan. I know you took 320, and I'm just like, are you taking 470? You haven't taken? No, you took 474 with someone else. Are you taking 475 with me? You just finished 474, right? So you've just finished data mining. And let's go ahead and write this equation right here. P hat minus P naught over P naught Q naught over N square root. And Q naught equals, so we're going to do 1 minus P naught. Awesome. 479, 476. That's some good classes right there. Great job, Alan. I am forever honored by, I just believe you're going to go on to do great things because you're already doing great things. You've already helped a bunch with the Discord and everything. So the capstone, the Python class, you're going to be doing a lot of like application. I think a lot of times, at least at the lower levels, it's hard to see how all of this applies because we're mainly just solving equations. But then at the upper levels, when you start, coding things, and you're just like solving problems, you're like, oh, now I can just like, someone asks a question, I can be like, let me go look at the data to see what the data says. And it's based on the backbone of what we're doing right here. Oh, you're welcome, Alan. No, it's, and I'm hoping, we get to swing by and see everybody, but yeah, I'm really honored by. Did we ever see each other on campus, Alan? Did we? I'm trying to remember. There was a student, it's probably a different student who I would see on campus, and he and I would talk about K-pop, but I don't think that was you. I mean, I obviously know who you are on Discord, everything we've talked on Discord, but I don't think you were the student who I would see and we would talk about K-pop. I think it's just a different student. All the K-pop stuff blends together. Let's see right here. I'm going to disappear. You won't be able to see me. And there we go. Oh, the bottom of the equation. We did my freshman year 3 years ago, but when I waved at you, oh, that's no. Because weren't you wearing a backpack and didn't you have like Blackpink or something on your backpack? That's the conversation we had on campus, right? Isn't that? Yeah, so that's what it is. That's what it is. You were in Alan Panel's class, and then you were walking to campus one day next to and I was like, hey, I know K-pop. I was like, I like that group. Was it Blackpink or something? I think it was. And then we just started talking. And like that's, I'm pretty sure, because I was like, I'm pretty sure that conversation was with you. And You're like, no, I don't got anything. No, it was another guy then. Um, it was another guy who had some K-pop stuff, and I was like, hey, I know that. Um, so it was totally different. When we testing, mean, how do we get this specific hypothesized value? It just wants a number that we want to do. Yep. Basically, pick a value and just say, I'm testing this value as true. Great question right there, Ritu. You'll test a specific value. We didn't start talking about K-pop until anything related to 320. There you go. That's so yeah. It was someone else then. It was another student. I'm trying to remember their name. But yeah, it's just tougher when I don't see everybody to like remember everyone. To be like, okay, wait, we had this conversation. It's harder to remember online conversations than it is in-person conversations, because in person, you actually like see the person. Online, you see a name, which is good, but it's harder to remember, like, like, okay, wait, because it just creates less of a memory. Everything kind of blurs. There we go. And there's the Z-score. Z-score is kind of, it's kind of small. It's very small, actually. What am I saying? Kind of small. Z-score is pretty small right here, actually. I can stop by and Lenny if you hold office hours at the same time. Yeah. Yeah, whatever works. I'm going to have a slightly different time because I'll start teaching 320 coming up here soon. So, Alan, if you hop in, you'll be talking to the 320 students. So join in. You don't have to, but you're always welcome to. And we could join on Discord or anything if you want. So I could talk to you about maybe setting up a Discord time so you could talk to the students. We're testing, is this unusually high? We want to test greater than. Test the assumptions and conditions. Here's the Z-score. Round to 2 decimals. Find the p-value. We go over to the David M. Lane applet. So the David M. Lane applet, Mubot will put that in the chat right here. Awesome. Thank you so much, Alan. Like, there's people I know who will just swing by to help out, and there's the p-value. And thank you so much, Alan. I appreciate that. Round to 4 decimals. So there you go. This p-value is not unusually high because the p-value, it's not unusually low because the p-value is high. So the p-value is high, and we don't talk that way. The p-value is too high to conclude that the death rate is unusually high. The p-value is high, so we don't reject the null. I wish they always kept the same wording, but they just want to see if you can understand it differently. But the p-value being high right here means we don't have enough evidence to reject the null. And even if we did, whether or not the death rate is caused by cancer or not, the cause cannot be determined. Boom, another 100 right there. I got my Z-score of 2.55. For my Z-score, I had 43 out of... That does about make sense. I'm looking at this right here. That seems pretty accurate right there. Let me think right here. My brain's working on it. Because I would think here's my Z-score. And I'm going to divide my Z-score by 15. Correct. No. And then I'm going to times it. Well, then, no. Undo. Times by 15. I should be able to find your Z-score. 4/15, and yours is the whole. Oh, so if I divide it by 4, and then times it by 15, no, it's not finding it. Wasn't your trick like if the p-value is high, let it fly? If it's low, reject null? You're exactly right. We were talking about that earlier. If the p-value is low, reject the null. If the p-value is high, just let it fly. Can you talk about the R-squared? And this is true. You bet, Leanne. We can go to that next. We've been doing some homework here. So, Caroline, tell me if you get it. I'm finding about that result for yours. Your sample size might be different than mine. So that's why I might, 230, yes. So your sample size is different. So your results are going to be a little different. 2.55 sounds about accurate. And Airline, you bet. We'll talk about the project here. Let's do a little project. And you can see Alan in the chat saying if the p-value is low, reject the null. If the p-value is high, just let it fly. You bet. Everyone is so awesome right here. So much positivity, helping out, remembering the phrases. And I really appreciate like how everyone's just like, oh yeah, we'll do this. Like we can do their question. We got this. Because we got so much time right now. Everyone's here so early today. Doing a lot of practice. I'm trying to find Canvas. I have lost Canvas. Let me reload Canvas. Online UTK. You know what? Isaac, I think, was in last year's mini-term class. And so him swinging by being like, whoa, some changes. Class looks way improved. A lot of things, a lot of new cool things. I'm always trying to improve between semesters. QQ, straight enough. No outliers. Plot doesn't thicken. Exactly, Alan. Exactly. Hopefully, you know, those are the conditions for regression. And I'm hoping people just can help remember them and help learn them. Let's go over here to this data set. No, I appreciate that, Alan. Oh, let's do this. Let's predict whether or not... Let's predict... We'll do something different. Oh, let's predict if someone will... No, we did that one. Let's predict diabetes. Okay. So we're going to do a decision tree right now on predicting... Yes, great job, Caroline. Caroline, let's throw some 50 points for Caroline right there, getting the question right. Excellent work, Caroline. That's what we're here to do, solve some problems. Let's hop over here and look at Leanne's question. So let's go here to analyze, and we're making a decision tree. So we're going to go to predictive model and partition. And Alan's done some advanced decision trees. So one thing you might not know, Alan, so this is how to do the 201. You can actually do the bootstrap trees and the boosted trees. 201, don't do these. You can do k-nearest neighbors, naive bayes. You can do all these right here, bootstrap trees, boosted trees, all that good stuff with tuning parameters. Jump actually has the tuning parameters, so Alan knows a bit about tuning parameters. We're not going to talk about that in 201, though. We're not going to include this because this is an identifier, so don't include that. We're going to click on one of these, and then we're going to hold Shift, and then we're going to click the bottom one. Now, mine has age group. I think yours has age group too. Did you mention you wanted to interpret in the sample tests when you talked about them in class? For the project, I think you need interpretations. Just make sure, look at the rubric and make sure whatever it asks you to interpret it. I know it's pretty cool that Jump has these things. Jump has some advanced features. Of course, coding will allow you to do more. Like, Jump's always trying to add new things. So it's got that option right there. And you got the validation portion if you want to do a holdout portion. So this is how you can do a holdout right here, and you've got how you handle missingness right there. So Jump, yeah, got some cool stuff. We're going to unclick this. Let me show you again. We're going to click one, hold Shift, and then we're going to hold Control to deselect this. You could, if you want, just grab all these and put them over here. This just takes longer. But all you're trying to do is just get all your X's over here. You get all your X's over here, every single X variable, and then you get your Y variable up here. So the goal of a decision tree is to let the algorithm do all the heavy lifting for you. You're going to take all of your categorical quantitative X's, no identifiers, and you're going to take your categorical or quantitative Y, whichever one you want to predict, and make your tree. With this, we have our tree. We're doing a categorical tree today. We did some quantitatives other days, but you'll notice right here, it looks like a mosaic plot, not wrong button right there. Looks like a mosaic plot, and you can see right here the people who have diabetes and the people who don't. Now, when I hit split right here, here's what it's going to do. It's going to start splitting people into groups. And you'll notice the best thing to tell if someone has diabetes or not, you pick, and the Y is just the one you want to understand. Like, why do people have diabetes? So why do people have this? Let's find out. Glucose, your blood glucose level. What else? Your glucose. It's doing this for me. What else? Your age. So who are the most, and we'll split right here again. Who are the most likely people to have diabetes in this tree? We'll split right here. This is going to be my tree. It's a rather big tree. I want you to look at this tree, and I want you to look at the categories and tell me who are the people who are most likely to have diabetes. And if you're having a hard time telling, it might be easier if we go to the leaf report. Under the leaf report, which is a pretty large leaf report, and you could use this one. You can see the percentages of people who have diabetes, and just take a look at this. This says glucose level is greater than or equal to this, and their glucose level is greater than or equal to this, and their glucose level is greater than or equal to this. Who do you think are the most likely people, which is this group over here? This is group 1. Like, how would you describe them? You could basically boil this down to just one characteristic, because it's like their glucose is greater than this, greater than this, greater than, or oh, is that less than? Oh, that's weird. Oh my gosh. Well, that made it a lot harder, because the last one here is they're between this level. That's so weird. You can split pretty much however you want. I'm okay with that. I want to see some uniqueness. I want to see what people do. The last picture we need right here is the split history. This is all under the red arrow. The split history shows us the increase to R squared. And one might argue I've split this too much. because especially right here, I'm not getting a good increase. So we might even bring the tree back to here. So one could argue I've split this tree too much because this is the history of the increase in r squared, which we'll interpret here in a second. I'm okay with however you want to interpret your tree, but you need a picture of this. Let's show what pictures you need. You will need a picture of this. There's a picture. Good picture of that right there. That's a picture. That is your tree, so we can see what's going on. And you've got your r squared up here, which we'll interpret right now. This r squared says 32.8% of the variation in people's diabetes is explained by the variables in the tree. 32.8% of the variation in whether or not people have diabetes is explained by the variables in the tree. And so I think technically, Layla, I think this is what's confusing. It'd be the people who have glucose levels between here and here. So the most likely group to have it are people who basically are contained within this. It would include people who are greater than or equal to this. Like it'd be inclusive of this. I guess if we go mathematical notation, the people who are most likely to have it according to this tree are inclusive of 166 up to 191. Does that make sense here, Layla? Which that was I don't know why it's the people. I mean, these people are still very likely to have it, but the most likely people are the people who are between. So this is the most likely group right here. And then the other group right there that I have highlighted is also pretty likely, but I know it's so weird, right? And then the leaf report also makes that kind of clear too. When you see they're greater than this, greater than equal to this, but then they're less than this. And so right here, the first row, yep. And so they would have greater than equal to this, greater than equal to this, but less than this. And the least likely people to have it, just think about this. Call these people, what sort of people, like age-wise, who have this, like, and you could basically describe this, like, I would say, well, the least likely people to have diabetes, which makes sense with our world. Could we split on the other side and observe those who are, yeah, let's do that. Let's go over here and even split this one a little more. So you could split this here. You'd have to take another picture of your tree. Yeah, this makes perfect sense. Think about this. The people who are least likely to have it are what type of people? Like they have low blood sugar, they're water, and they're water in shape. We would assume with body fat. So I would describe these people as, you could do it mathematically or with the notes right here. You could say these people have glucose levels less than 128, they're less than 29 years old, and they also have body fat less than 30% body fat or whatever we're measuring right there, 30 BMI. It's all right. Don't worry if you're like, what is this exactly? I'm just going to call it BMI for the moment. And with this right here, you can see they have low blood sugar, they are younger, and they're more in shape. They have less body fat. And yeah, this group right here is the least likely to have it, with only 3.16% having it. And so there's only 3 out of 100 right there. So a very, very small percentage, that little tiny blue blip right there, are the people who have diabetes in this group. Does that make sense right here? Is this making sense? And now we're up to 34.7% of the variation in diabetes being explained. And you can see, you don't technically need a picture of this top part, but you can see the groups splitting apart, where this is the group that's very unlikely to have it. There's the 3 people who do have it. Here's the group who is most likely to have it, and that's where the 2 people, is that only 2 people right there? That's 2 out of the 38, I believe. There's the 2 out of the 38. And is this making more sense right here, Leanne? It looks like a lot of output, but as you break it down, hopefully it's making sense. So that's how to analyze the decision tree right here and talk through the output and make sense of it. So any last questions on this right here, just as we go through this output and try to make sense of it all and see what's going on? This is how to analyze and interpret the decision tree. So would you say 34.7% of, or 34.7% of the variation? I would just add variation. Let me switch this. Of the variation is explained by, not just by, there you go. 34.7% of the variation in having diabetes is explained by the variables in the tree. Does that make sense right there? 34.7% of the variation in having diabetes, which is a lot of the variation, is explained by the variables in the tree. So these variables right here help us understand the reasons or the pathways on whether someone does not have it, the people who are kind of iffy on having it. This group, no, it's a little more. It's leaf number 4, so it's like 6% right there. But they're unlikely to have. These are people with slightly moderate glucose levels, and they are younger. Yeah. So you can see basically age is a big factor. Age kind of comes into play here. Glucose is a huge factor, and body fat comes into play. But mainly the most important factor we see throughout this is glucose. It just makes sense. I mean, sometimes you do statistics and you're like, yeah, that just kind of confirms what I knew about the world, that glucose is one of those things that is impactful on whether or not you have diabetes or not. Like, it's like, wow, shocker. But we let the tree do the work for us right here. And I think let's hop back here to space. Time to go to space. Let's do this. Okay. Let's see. I think we got Caroline's question. Let's go here. I think Layla said, can we do the one in airlines public relations? Or I think there was one more. I think we put your question in the chat. Yeah, no, Layla asked about it. There we go. So here we're going to do Layla's question, public relations. In airlines public relations. Is it about the lost luggage? I think it is. Here we go. Let's do this. I've made a mistake on this one before. I'm like, oh no, we got this. Excellent work on the points here. Let's throw out another 50 points. Office hours points. Let's make it happen, Mubot. Show everyone their points. Okay. Excellent work, Layla. Are the assumptions and the condition met for a z-test? And this is a one proportion z-test. So what we have right here is we need to randomly select observations. Sure. Assume random. Alan's got crazy points. And we need to select less than 10% of the population. Well, 152 would be less than 10% of all passengers. And we need there to be at least 10% successes, at least 10% failures. And so with 89 as the null, that would mean we'd expect 135. I love Alan's level right there. And then we would take here Q naught and times it by this. That's NP naught and Q naught. And yes, the conditions are met. There's at least 10 successes, at least 10 failures. And so state the null and alternative hypothesis. So the null has the equal sign. Dun, dun, dun. So the tough part of this question, I have to want to click the show completed just so I know that we're not going the wrong way on this, is we're trying to show... We're trying to show that it's less than this. Because the airline, we're trying to cast doubt on it to show that the airline has less luggage than, like, they're losing more luggage, returning less luggage than they say they're returning. They say they return luggage 89% of the time within 24 hours. We observe them returning luggage 70 times out of 152 within 24 hours. So we're trying to cast doubt on that to say, nah, we got evidence to show it less than that. So we're trying to show the alternative that the true proportion of time they return the luggage, that's what P stands for, is less than 89%. And since the assumptions and conditions are met, we can get the z-score. Let's go find that z-score. Now, it should be good. It's going to be a very... Remember, they're claiming 89%. So Layla, tell me one bit of the notation right here, Layla. Tell me one bit of the notation as I write out the equation right here. Tell me any of the notation. I'm going to circle it, and they're claiming 89%. So we need the notation. What is the notation? P hat minus P naught over P naught. Q naught, because we're doing the one proportion. Oh. P naught, Q naught over N square root. And so there we go. So what is the notation? What do we have up here? Notation-wise, what do we have? Any bit of the notation. Sometimes you're given X over N. Sometimes you're given it. What all notation-wise do we have? Let's see. I might give estimates. P naught, exactly. P naught is this. This is P naught. And since that is P naught, well, once you find P naught, you can find Q naught. Very important. This is X. This is N. And so we can get right here that X over N. I'll have to go. Yeah, anytime. Anytime, Alan. So good to see you. Thank you so much for swinging by. And yep, which is just think about this. The airline, I want you to solve the rest of this, Layla, with just like common sense. Like, we don't do statistics by common sense, but I want you to just think through it. If an airline claims they return 89% of luggage on time and you see them returning less than 50%, what would you do to that claim of them returning 80% on time? The airline is saying they return 80% on time, 89% on time, and you observe them only returning. I always feel like you're saying peanut. You say peanut. That's too funny right there. What would you do to that claim? So I would reject it. Yeah, we'll see this here in a moment, which means the z-score is going to be pretty crazy. The z-score right here is going to be pretty extreme, and the p-value is going to be ridiculously small. So let's double check. Oh, there we go. There's all the decimals on that. So we get here peanut times square root. There's that. And then 70. I always carry all my decimals just in case. I hope I didn't make an error right there. Well, we'll find out. So here we are, negative 16.92. That's ridiculous. That is absolutely insane. So we're going to take that and just drop that right in here, round to 2 decimals. Now, we could plot this, but the answer is 0. Because visually speaking, all of our applets are not really even going to show us a good picture of this. This is negative 16.22, and that means we are, I can't even draw it like that, I have to draw it like this. We are down here at negative 16.22. We are just out there, way off the curve, and here's our p-value. That doesn't even do it justice. You can't see it. The curve is asymptotic. It goes towards... all right. You're welcome, Reese. Great job. I hope you got everything done. Great job, Reese. Cracking me up right there. So the p-value is 0, basically. The applets are not going to show it. You just go right here, the David M. Lane, or you go to this applet, and you type in a z-score of negative 16.22, and then you do left tail, which is below, and it's just going to say 0. And if we were to go to the David M. Lane's going to do the same thing. It's just going to not show any area below it because it's just basically an impossible. It's not impossible. I shouldn't say that. We can go over here to R and have it calculate the p-value. Do PT negative 16. No. P norm. Negative 16.22. And that it's ridiculous. It's basically like this right here. How close was I to it? No, I went way too far. Oh, come on. This is our p-value. To put it in context for everybody, that's our p-value. So if you want to see the p-value, that's your p-value right there. That is the p-value that is basically 0, telling you what you observed is basically impossible. And this is why when you go to these applets, we got the David M. Lane in the chat right here. When we go below a z-score of this right here and we plug it in, it's that. Ooh, it's even lower. So in truth, it's even smaller than this. I forgot the 9 right there. Oh my gosh. So... and then we need to go 1, 2, 3, 4, 5. Oh. There's the p-value right there. That's the p-value. And the applet is going to just show you this right here. It's going to say the p-value is 0. Because it's like you don't really need to know that it's this. It's 0. For all intents and purposes, we're saying that this result is nearly impossible by random chance. And that's why we're just entering in 0. Does the survey cast doubt on their claims? I think Layla was pointing out earlier. Yes, it does cast doubts. Yes, since the null is rejected, we are casting doubts, and that should do it. Boom, got that another 100 right there. Layla, great work. Does that make sense? You're like, this just does not seem possible. Visually speaking, and we drew it out right here, there's the p-value right there. which that's the percent of time this would occur by random chance, given 89% is the truth. And that is the area, if you're wondering, we had to use a program to calculate it because all the applets are basically calling that 0. It's so small that my picture does not do it justice. It's nothing, basically. We have to use calculators like this to calculate it, not, unfortunately, applets like this, because the applet's just going to be like, well, that's 0, and you can't even see it visually. So I wonder if you know what we might do for a little fun? I bet I could make my applet show it. I bet I could. And do I have my applet up right now? I think I do. I think I could fix my applet to show it. Let's see right here. This is my applet that I in part created. I got to give shout outs to Drew, PhD candidate. I think he did computer science. He wrote this in Perl originally, and then he started making adjustments and wrote it to Shiny. If I go here, I should be able to make adjustments on the normal curve. So this is a server. There we go. There we go. So we're literally going to have to go out to plus or minus 17 standard deviations. And sure, why not? Is that doing it now? No. That's not doing it. Is the p-value the probability of seeing sample zones? Yes. The p-value is the probability of seeing a sample result or one more extreme given the null is true. It's conditional on the null being true. That's exactly correct. Well, it's not liking that. Okay. That's not going to do it right there. We might be able to do it with this. We may have done it. Let's run the applet. No. It's just destroying the scale on it. Give it one more shot right here. I want to get to work. If you have a question, let me know. I'm just trying to mess with my applet right now. Say, Brian, you can't fix the applet. And I say, no. I want to make it show it. And I think... Okay, so that won't do it right there. And the UI is just what we input. So the UI is not going to do it. It would have to be over here. And that's where we're going out the standard deviations. Oh, wait. Okay. Here we go. I think this might do it. Yep. Here we go. Let's break it. There we go. Here we go. So now we can actually see it. You won't be able to see it still. It's not... This is what I drew. I was drawing this out a moment ago. And I can get my numbers actually on here now. So now we can go down to the other portion of it and get the numbers on here. So here's where I can put in my numbers. So here's this. This will actually put in the numbers now. And you won't be able to see it. It's so small. I could add like a red line or something. But the red line would have to actually extend over it. So now we'll be able to at least see where the numbers are at. So now we can see it better. If I got a part of multiple question wrong, is it worth redoing? Yeah, give it a shot. Give it a shot. And see how you do. And so this Layla right here, for all this work, we're just trying to show that below, here's the z-score we got. We're going to go below this value, and you just can't even see it. And my applet allows you to enter in all the decimals. It'll give you p-values that are very, very small. Like if you enter in below -4, it'll give you the p-value right there. So you can give it to more decimals, like you can ask for 8 decimals or 14 decimals. So you can ask for a bunch of decimals. So the quizzes, keep your high score. Yep. it keeps the highest score. It keeps the highest score. And you can see right here, it's starting to get so small that after a while, it just calls it 0. Yeah, and it is pretty cool. And we are able to, I wish I should put where I could make it drop a red line right here if I worked on this more. I could have like an add line with the input. So I just have to code in that it creates a line wherever you do it. Like it could say like observed result right here. It's saying the area is equal to 0, but yeah. And so it gives you much better, finer results. So you can see you can ask for how many decimals you want. So if the question said round it to 4 decimals, you could just do that and it would round it to 4 decimals. If it says 7 decimals, you can round it to 7 and you can get like exact answers and you can do value from an area. But I'm of course just messing with the applet right here. I'm going to switch it back. But it's just good practice on coding. And this is kind of the fun of it. Like we can make our own applets right here that are then going to find these areas for us and do everything for us. And this is the way it's meant to look normally, this applet I created. We put this on the Stat 1 website, and then there was a problem that so many students were using it that it crashed it. And you do notice it goes out to 4 standard deviations. I just didn't label the 4th because usually you just see 3 labeled. What's really cool also about this applet is that the screen will change sizes. So if you put it to a different size of the screen, it'll change sizes and make the applet. So I don't know, maybe one of these days this won't transfer to phone, but I wish there's already a phone app for the standard normal curve. But yeah, it's just like your David M. Lane with the buttons right here. And then you put in your mean or standard deviation, your significant digits. You can switch to the area. So you could pick something like a 90% confidence interval, and you could get the z-score for it by going between. And you can see the z-score for a 90% confidence interval, and you could put it to 3 decimal digits, is 1.645, and there's the 90%. I was also going to put in options. You could change the color and stuff, but generally pretty good applet. Maybe I should release it. I don't know. I really need to. I need to accredit Drew because he put a lot of work into this, and then I kind of learned from it and built on top of it. So thank you to Drew. If I put this out there for people to look at and work with and make better, I'd want people to know Drew. Like he's the one who got it all started, because at that point in my coding life, I don't know. The things I just did, I wouldn't have been able to do anyways. I'd be like, how do I change this? Where do I change this? What's this? But it's just practice. Let's hop here to space. What questions do people have? It is open floor for questions. Brian's having some fun working on the applet right here. See, I know what I need to do. I need to make a reactive vertical line that takes the input of the mean, or takes the input of the value someone puts in. So it'd be a reactive V line. So be reactive V line. I know the code I need to do. I just need to work more with Shiny apps. Create a Shiny app. They said project stuff left to do. Awesome. What are you working on the project, Layla? I'm sure people would love to see some parts of the project. So ask anything you're working on with the project. Great job. Has anyone turned in I don't think anyone's turned in the project yet. I sent my graphs on Discord. Do you mind looking at? Of course. We got time right now during off stars. Let me take a look, Ritu. There we go. I see your... Okay. Yes. Great job on the decision tree right there. I see you've got your splits. That is excellent right there. I see everything. You've got your R squared outputs. You've got your tree. You're predicting whether or not people have... Is it diabetes? I like it. You changed the title. I looked at how is diabetes associated with age and BMI. And you've got here age and BMI, such that we can see the younger people with lower BMIs are less likely to have diabetes, or the older people with higher BMIs. So definitely something going on right there. You've got, there's the R squared, 19.1% of the variation. Awesome. I'm not flowing down the project. You mind going over the graphs? Let me see if you have anything wrong with the graphs. Okay. We're on space, right? If you have questions, let me know. I'm going to look over Ritu's stuff. And let's take a look. I'd maybe if you need help, I'd make sure they're organized a little bit more. So one thing you can do, just move them around a little bit. You can I'm trying to think if you want me to show this. There's a button you can click on them where you can go to like wrap, organize them a little bit more, because right now they're all kind of, I would organize them, but I think you have everything. And maybe just the last one's good. I'd maybe just organize them a little bit more, like separate them. That's my only thing. Great graphs. Organize a little more in the paper. You know what? If you want Ritu, do you like making PowerPoints, Ritu? A lot of people have turned in PowerPoints. Yeah, definitely. Send yours when it's finished. The 2 sample T one. Yeah, if you want to, if you want me to talk about that, I can. If you want to make a PowerPoint, you can. If it's easier to organize and talk about something on a slide, that's quite fine to do also. Just make sure all the graphics aren't just like boom. You could also do them one by one. You can do PowerPoint if you want. Totally fine. You know, like if you do something that, if you did something way different, like if you did like a, I don't even know, I'd be like, can you maybe make some changes here? Yep. Yeah, let's talk about the 2 sample T. I think you're saying, let's go over and talk about the 2 sample T. So let's go ahead over here and talk about that 2 sample T test. With the 2 sample T test. The 2 sample T test. Let's go take a look at it. The 2 sample T test, we'll use the retention data set. Okay, let's hop here to the 2 sample T test. And 2 sample T test, let's do this. Do you want to do a 1 sample or 2 sample? 1 sample or 2 sample? 1 sample or 2 sample? We can do a 1 sample or 2 sample. Does the t-test? I think it was fine. As long as you hypothesize a value, you're good. I think we did 1 sample earlier. We did a 2 sample during class. Let's do a 2 sample right here, and a 2 sample t-test takes a categorical variable. We'll be doing this in depth tomorrow. I do have videos going over it. It can just be a value you make up, and then you can see whether or not you reject that value. We did that earlier. That's what we did earlier. So we want to look at, do people who churn make, and that means they leave their contract. Like, the people leave the contract. Do they make more or less purchases than the people who do not churn? So we're going to look at the number of purchases versus whether or not people leave their contract. So we have right here, did someone leave their contract? Yes or no. That's what churn means. And then the number of purchases they made. And you notice here, it looks uniform. You don't have to do this, but there should be a display option. You can actually look at the histograms on this. It is kind of uniform. These are both pretty uniform right here. A little bit of unimodality. Yeah, it's uniformish. It's just hard to see with the points being all clustered up right there. Let's do the t-test. And what do we see? This is rather interesting, actually. How do you interpret this? This is the main thing to interpret right here. This is the main thing to interpret. This just shows you the shape of each of these groups. Like the no group is mainly uniform. Like a slight, this is more uniform. Does that make sense, Leia, how I'm looking at this? Like this is the distribution from 0 to 20 of the no group. A little more built up here in the center. And the yes group is about the same-ish. But both of them are kind of uniform. Like they're flat. Like not any really sharp modality to it between uniform and unimodal. We don't have to interpret that. What we want to look at is the difference right here. This is the key part right here where we see the difference. This difference right here shows us who made more purchases, the people who churned or the people who did not churn. And this means they left our company. They went to a different contract. They said, we're leaving our cell phone contract. Who made more purchases on average? And it might be easier to see if I show you this. Don't include this one, I wouldn't. But can you see which one made more purchases now? Which group, the no or the yes group, made more purchases? And I'll show you how I know that from the other output in a moment. So N or Y in the chat, was it the no or the yes group that made more purchases on average? So you should be able to clearly see it in the output now. And then I'll show you how I know it from the other one. People who did not, exactly. We're not going to use that output though. We're going to use this one. And if you notice right here, the difference is negative. Do you see, since the difference is negative, that would be associated with the no group right here. Does that make sense, Layla? That the no group had a higher mean because when we do yes minus no, we get a negative number. So if this difference right here is negative, then the second group was higher. Exactly. Since it's negative, then the difference, the no group had a higher average because we see a difference when we do yes minus no, where we get a negative difference. Yep. And so that's what that negative difference means. But this negative difference between the two, or this difference between the two groups and how much they purchase, is probably just due to what? And this is where this important number comes into play right here. This difference between the two groups is what? This difference between the two groups, because this is the does not equals test. The difference, this is the big thing. If you're doing the test, which I think we're doing the test, the difference between the two groups is likely what? By random chance. Because we think the difference between the two groups could be somewhere between this amount and this amount. What do you notice is contained in this interval, a value that is believable, which is interestingly enough related to the null hypothesis? What value is contained in that interval, which would make you think, since we're not rejecting the null, what value? Because we're testing two means to see if there's, on average, people who churn make more purchases, or on average, people who don't churn make more purchases. Is there a difference? What value is contained in that interval? So you would say, well, that's contained in the interval, and we're testing to see if there's a difference, and we don't reject that value. So I don't think there's a difference because it's believable to me that the difference could be this. And so I'll put the words in there in a moment. So for this, are you just comparing the numbers on the side to that? Well, this is your interval. This is your confidence interval over here. This is the confidence interval. And this over here is the test over here. That's the does not equals test, which we'll do the does not equals test. So that's the confidence interval, where we think the true difference between the groups is somewhere between the no group making 1.7 more purchases on average to the yes group making 0.34 purchases more on average. So it could be that the no group makes more purchases, or it could be that the yes group makes more purchases, which means the true difference might be what between these groups? So it could be that the no group makes a little bit more purchases. It could be that the yes group makes a little bit more purchases, or it could just be that the difference between the groups is what? So it could be the no group makes more purchases, could be the yes group makes more purchases. With that in mind, the true difference between the two groups could be just this. It seems believable to me at this point, because I'm saying it might be that the no group makes this many more purchases, because that's the negative difference, or it could be that the yes group makes up to this many more purchases, because that's the positive possible difference. So somewhere between the no group making 1.7 more purchases on average to up to the yes group making 0.34 more purchases on averages, I'm 95% confident that the truth is somewhere in there. That maybe it's the yes group makes more purchases, maybe the no group makes more purchases, but I'm also saying that the difference could be what between these groups? So what value am I saying could be the difference between these groups? So I'm saying it's very, very possible that the difference between these two groups could just be this, because they got the null right there, and we don't reject the null. So since we don't reject the null, that means it's believable that the difference between the two groups could be what? And just think it's in the interval. What is inside the interval that we're not rejecting with the test? What value for the difference that we're testing between the two groups? We can do an obvious one here in a moment. The value is 0. So we are saying, do we think there's a 0 difference between the groups? Yeah, I'd say it's possible, because 0 is in the interval and we don't reject 0 as a value. Let's do one that's going to be super obvious. Do you think men and women are the same height? Do you think that men and women are the same height? Just want you to think about that for a moment. If I told you men and women are the same height, on average, men and women are the same height, would you be like, I believe that? Or you'd be like, yeah, I don't believe that, Brian. Let's go right here. What are you supposed to do about the 0.19? Where was the 0.19 at? Let me see here. 0.19. Oh, that's the p-value. Since the p-value is above 0.05, we fail to reject the null at the 0.05. And yet some women are taller than men, some men are shorter than women. It all depends. But with the average man, so we're talking about on average, and that's a good way of pointing out right there. We're not saying in all instances, and that's an important thing for statistics. It's not like we're saying all the time this. We're saying, do we believe on average that men and women are the same height? And that's the null hypothesis, that they are the same height. And what would you do to the null hypothesis that on average, and you can just see here data we collected, what do you think rationally you would do to the null hypothesis that men and women are the same height? What would you kind of rationally do if someone said to you, men and women are the same height on average? Not like men are always taller than women, because that's nonsense. But if someone said on average, men and women are the same height, like there's no difference between the average height of men and women. You'd say like, hey, I got some data right here. Let's investigate that claim. If someone said on average, because that's what statistics look at, individuals can have a lot of variation in them. I'd reject that claim too. And let's look at it statistically here. So there's the p-value. So you notice right here, here's our observed result, and here's the p-value. And this kind of makes sense. If you think about it, what if I told you the claim, if I said, I think on average, men are about 6 inches taller than women. Like the average male is about 6 inches taller than the average woman. And that's just average. It's not like saying men are always 6 inches taller. But on average, men are about 6 inches taller than women. And that's within the interval. I am 95% confident that the true difference between males and females' heights is contained in the interval 5.7 to 6.7. And so where men are taller. So I think, yep, we were doing some chapter 15 earlier. If you have one, AJ, feel free to ask. Definitely, we were doing some chapter 15 earlier. What do you say about the upper and lower of the confidence interval? What is it telling us? Oh, is that making sense right here, Layla, as I interpret it? Since the difference is positive, the first number is bigger. Does that make sense, Layla? Like, since the male is right here, male minus female being positive indicates that the male mean is higher. So because it's the first number, the difference is not negative. So I am 95% confident that the true difference between males and females' height is contained in the interval 5.7 to 6.7, where males are on average taller than females. Like, not saying they will be, but we think this is what the true difference might be. I also reject that there is not a difference. I have evidence that there is a difference with this right here, because this would test that there is no difference between the two means. Is this making more sense right here, Layla, on how to interpret this? This one is a reverse of it, where we don't reject the null. So if it was negative, what would you say? So we could do a negative one. Let's do GPA. The women went out on GPA. So let's test out gender, and let's go here to, why is GPA categorical? Must have been when I copied it. That's not good. If you see. Good. I don't know why GPA was categorical. GPA is not categorical. I hope that's not in your guys' data set like that. If you get something weird like that, tell me, because that would have made a mosaic plot. Okay, there we go. Okay, so the difference here is negative. So how would you interpret this here, Layla? How would you interpret this with a negative difference? So since this has a negative difference, what does this mean right here? With a negative difference, what does this mean? The negative difference. So I'd say I'm 95% confident the true difference between males and females' GPAs. Well, and we did observe males having a lower GPA by 0.178. So that's what we observed in our sample. This is the sample difference right here. So that's what we observed in the sample. And I'm 95% confident the true difference between, and I would be confident that males on average have lower GPAs than females, like on average, not saying all males have lower GPAs, because you can see here, this male had a very high GPA. That male had a 4.0, and this female had that's probably closer to my GPA, a 0.8. So the lowest GPA out of everybody was someone who was female. And but on average, males had lower GPAs by 0.78 because the negative difference means the female mean was higher. And we say, I'm 95% confident the true difference between males and females' GPAs is contained in the interval negative 0.105 to negative 1.06 to negative 0.25. With the difference being negative, this indicates that we believe females have a higher mean than males on average. Does that make sense? And we also reject that there is not a difference because 0 is not contained in the interval. So by 0 not being contained, we think there is a difference that on average females have higher GPAs than males. Does this make more sense, Layla, as we go through another interpretation of it? And if you have more questions, ask. Let me know. But great work right there. Great practice. So this would be good evidence that females have higher GPAs than males. Doesn't mean all. Just means on average. And you can see the averages right here. I wouldn't include this output. Maybe we do that. You know what? I kind of like that. Yeah, so I think I might have, yeah, definitely. If you want to look over your interpretation, I wouldn't include, we don't do the ANOVA. The ANOVA is a bit different of a test. It does have an R squared, which is 3.6% of the variation. And it does a pooled t-test, which is done mathematically differently. It's similar-esque, and you also get to see the means right here, which we see females had a higher mean than males. So, hey, Leslie, good to see you here. Thank you, Leslie, for swinging by saying hey. So good to see everybody. Yes, let me know if you have questions. Let's up here to space. And let's do this. Let's throw out some 50 points. Leslie swinging by right here. Ritu asked a question. Organized into PowerPoint and things good enough, but could you... Yeah, of course. I see. Exactly. Short hair Brian. We're gonna have man bun Brian up here though. So short hair Brian is here for a while. 6 months from now, he won't be short hair Brian. So short hair for now. A little bit long hair right there. Short hair Brian for now. But great stuff right there. Excellent work. If you have questions, let me know. Ritu, definitely send it my way. I got 9 messages right now. Let me take a look. Ritu's got the PowerPoint here. Let me see. Let me see. I might have done it. Whatever works best. I'm not too critical on stuff. I think so, yeah. Yep. I like that how you did the decision tree continued. Yeah, and then just explain it afterwards. Yeah, I like this better. I like this a lot better. Yeah, this is great. That's great. We're not going for perfect. That's great. Don't worry. Everyone's perfect is different. But that's really good, Ritu. I think that looks way better. It's way easier. Like, if you're presenting that in a meeting, the graphics are way bigger. You're like, here's the one sample t-test. Here's what we have. Now let's talk about the results. Way better, Ritu. Great stuff right there. So the one sample t-test is the one where there was one y and the rest were x's. The one sample t-test is going to be where there's just a quantitative, where you do analyze distribution. So you'll do analyze distribution, and you're just doing one quantitative y variable. Here, I'll put the video in the chat. Here's the video in the chat. There we go. So the one sample t-test is just one quantitative y variable. The one sample t-test is one macroeconomics crash course. Oh, I mean, they got a good video right here. What in the world? What in the world am I watching? I've never heard of it. Crash Course got 12.3 million subs. Yeah, Decision Tree one. Yeah, you're talking about Decision Tree, exactly. Man, Crash Course. Intro to Psychology Crash Course. 10 minutes. 10 minutes? 10 minutes? Can you explain what we're looking for in the last part of Task 2? Let me take a look at that. Definitely. Let's go take a look. I was looking at these crash courses right here. Mini-term project 2. Okay. It's loading up. Let me download it right here. Let's get it on the screen. And are you talking about the one sample T? I should put that on a separate page. Let me go down. Put on a separate page. Okay, let's go to the main screen. And so are you talking about Ritu last part of task 2? I think task 2 is the one sample T. Okay. So create a one sample T test, include the output showing the distribution with the summary statistics in one of the pictures. Also include a separate picture of the confidence interval. Finally, so you need to show the test also. Finally, include a value your company wants to test as a hypothesized test value. Interpret to the rear the confidence interval. Next, explain to the rear the results of the does not equals test. Finally, explain how the confidence interval and the test results come to the same conclusion. So what are we talking about right here? How would a confidence interval and a test result come to the same conclusion? So how does a confidence interval and a test come to the same conclusion? Let's go back to the notes from today. How do they come to the same conclusion? How can we use a confidence interval and a test to see if they come to the same conclusion? So how can we use a confidence interval and a test to see if they come to the same conclusion? So what can we do? So if we look at an interval and the interval does not contain the value, what can you do to the value? If the interval does not contain the value, what can you do to the value? if the interval does not contain the value, what can you do to the value? So if the interval does not contain the value, what can you do to the value? So you see right here, I made a confidence interval that goes from 400 to 600. I'm testing the value of 900, which would be further over here. My test is 900 right there. So what would I do to the value of 900 if 900 is what I am doing? What would I do to that null hypothesis? Because 900 is not contained in my interval. We would reject the value exactly. And then we have evidence that the truth is not equal to. So anything inside a confidence interval can be not rejected at 1 minus confidence interval level of alpha. So if we're doing a 95% confidence interval and something is inside of it, we can't reject it at the 0.05 level on a two-sided test. So we're doing the two-sided. But if something's outside of it, we can reject it. And we see the same thing right here where things are outside the interval or things are inside the interval and we cannot reject it. So definitely right here, we see the idea of, can we reject something at the 0.03 alpha level? And no, we cannot, because the p-value is above 0.03, and it would also be contained within a 97% confidence interval. The 97% confidence interval right here has a 0.03 alpha level test connected to it, because a confidence interval and a test will come to the same conclusion. So confidence intervals and tests come to the same conclusion when you use the two-sided test or the confidence interval. They come to the same conclusion. If it's contained within the confidence interval, you cannot reject it. If it's outside the confidence interval, you can reject it. Does that make sense right there, Ritu? Sorry to space. Does that make sense how to go through those results right there and talk about, did your confidence interval contain the value? Did you reject it? How does this relate right here? How does a confidence interval relate to doing a test, like the mechanics? Yeah, it's under looking at the mechanics, like what decision did you make with your test? How does that relate to your results of your confidence interval? And explaining to the reader, like, here's my confidence interval, here's my test, and this is why I can or cannot reject it. Awesome work. Great stuff. Well, if you have questions, I'm going to answer some more Discord here in a moment. Take a break for a moment. But great work, everybody. Keep up the great work. We'll be back here. Email me if you're stuck. Discord me if you're stuck. I'm going to take a little break. We'll be back. I'll see everyone tomorrow. Bye for now, everyone. Bye. You're welcome, Layla. Great job, Ritu, and everyone. Bye for now.